Welcome to This Explainer. You know, there is this absolutely fascinating paradox sitting right at the heart of the renewable energy industry. When we look up at a solar panel gleaming in the sun, we naturally think about clean, dry, infinite energy, right? We envision a future completely free from the messy extraction of fossil fuels. But the reality of actually creating those sleek, silent panels involves a massive, complex, and highly sensitive industrial supply chain. Today, we're diving specifically into the environmental accounting standards developed for solar technology and project developers. And we're going to uncover a hidden dependency that is absolutely crucial to the entire industry. It's a challenge that takes incredible engineering and foresight to manage.
To kick things off, let me ask you a question. What do you think is the secret ingredient behind harnessing solar power? Seriously, if you were to walk into a manufacturing facility today, past all the polysilicon, the metals, the glass, what is the one resource that the whole operation hinges on? I'll give you a hint. You might be surprised to learn that it isn't a rare earth metal or some proprietary chemical compound.
The answer is actually water, but not just any water, ultra-pure water. The solar technology industry is heavily dependent on massive volumes of it. See, manufacturing solar photovoltaic panels, especially cleaning the silicon wafers and components, is incredibly water-intensive, and it has to be stripped of virtually all minerals, dissolved solids, and impurities. It is a critical input in some of the most sensitive processes on the factory floor. Without huge amounts of this highly refined water, the advanced solar panels that power our homes and grids simply could not be produced to the standards required.
Let's look at Section 1, the solar paradox.
This brings us to a really captivating contrast. We've got a clean, dry energy solution generating electricity out in the desert on one hand, and a highly water-intensive manufacturing process on the other. This dynamic between the arid, sun-drenched environments where solar panels operate best and the fluid, resource-intensive reality of how they are actually created is what we call the solar paradox. The sustainability accounting standards specifically highlight this. The manufacturing process doesn't just use water, it transforms it. And dealing with that transformation, like treating the water and securing its steady supply, is one of the most pressing sustainability challenges solar developers face today. It's a complex balancing act between environmental goals and absolute operational necessities.
Moving on to Section 2, the need for ultra-pure water.
If we actually zoom in and follow the life cycle of a single drop of water on the factory floor, it starts with Step 1, withdrawal. Solar manufacturers draw water from various local sources, surface water like rivers and lakes, groundwater, rainwater, or just municipal water supplies. Step 2 is ultra-purification, where they treat that raw water until it's perfectly clean for manufacturing. Then, in Step 3, it's used directly in the fabrication of the solar PV panels. But Step 4 is where things get really complicated. This process generates a massive amount of wastewater. The industry standards mandate that this wastewater has to be rigorously treated before it can be disposed of or reused. And that treatment process inherently results in incremental operating costs and requires significant capital expenditures for advanced filtration infrastructure.
Next up is Section 3, the threat of water stress.
So what happens when that drop of water we just traced becomes scarce in the local environment? According to the WRI Aqueduct tool, which is a major global database used to map water risk, an extremely high baseline water stress occurs when over 80% of available water in a region is consumed by agricultural, municipal, and industrial users. 80%. This is a vital metric. The sustainability accounting standards literally require solar tech entities to analyze all of their operations and disclose exactly what percentage of their water is withdrawn and consumed in these high or extremely high stress regions. Imagine running a thirsty factory in an area where 80% of the water is already spoken for. The margin for error is virtually zero.
Operating in these water stress regions introduces immense environmental and financial constraints. We are talking about severe drought, seasonal variability, and the compounding impacts of climate change. For the factory, this translates into acute regulatory and financial risks. Companies can face extreme volatility in water costs. On top of that, local governments might impose strict restrictions on water withdrawals, or the factory might face constraints on its ability to even obtain or retain basic water rights and permits. Bottom line, if you can't get the water, you can't make the panels.
Now for Section 4, tensions with communities.
Let's step outside the factory doors for a second, because this is where the environmental data becomes a very real human issue. The Sustainability Accounting Standard formally recognizes this exact risk, noting that industrial water resource use may generate tension with local water users. Think about it. When a solar manufacturing plant pulls massive amounts of water from the same dwindling aquifer that a local town relies on for drinking water, or that local farmers rely on for their crops, well, the potential for serious conflict goes way up.
This tension isn't just theoretical, it translates directly into hard business risks. If community concerns escalate to regulatory agencies, it can lead to immediate operational disruptions, literally shutting down the manufacturing line. It also drives up operating costs as companies scramble for alternative water sources. Furthermore, the reputational damage can be devastating. A company producing green technology to save the planet simply cannot afford the adverse impact on its brand value that comes from depleting a local community's water supply. It entirely undermines their core mission and standing in the market.
Finally, Section 5, Sustainable Strategies and Solutions. So how does the solar industry actually mitigate these immense challenges? How do they ensure long-term scalable sustainability without running dry or alienating their neighbors? Well, companies are actively investing in innovative engineering solutions to efficiently shrink their water footprint. They are deploying process water recycling to drastically reduce the sheer volume of water they need to withdraw from local sources. They are designing closed-loop systems that continuously filter and reuse the same water, aiming to minimize or even entirely eliminate wastewater discharge. And they're relentlessly pursuing improved production techniques to lower the overall water intensity required to produce a single solar panel. They even use advanced tools like the World Wildlife Fund Water Risk Filter to map and manage these opportunities on a global scale.
But this leaves us with a really complex reality to wrap up this explainer. The accounting standards specifically ask companies to disclose whether their water management practices result in other life cycle impacts. Because as you might guess, running intense, closed-loop water recycling systems requires a massive amount of energy. So we have to ask, are we simply trading a water scarcity problem for an increased greenhouse gas emissions problem? Solving one environmental challenge often requires carefully balancing trade-offs across the entire manufacturing life cycle. It's a fascinating reminder that in the transition to renewable energy, every single drop and every single watt truly counts.